will talk today about how to achieve the perfect quality in flat steel production, but not only, by using this advanced surface inspection. You all have received the agenda, so we will spend about 1 hour, 1 hour and a half together. And our speakers, we have several speakers, will have the opportunity to present their works and the results of the project Defect Inspect. As I said, the session will be recorded, so you will receive the link later. But before starting with the workshop, I would like to mention that this workshop is supported by WOLAB. WOLAB is one of the more than 100 European digital innovation hubs. It is an initiative of Digital Europe. It is co-founded by the European Commission and the Wallonia region, and it is also part of the Industry of the Future program supported by Digital Wallonia. WOLAB as a mission is to help small and medium manufacturing companies to implement digital innovation. WOLAB focus on key technologies like artificial intelligence, like high-performance calculators, cybersecurity, and the Internet of Things, and provides services like technological demonstration, individual coaching, assessment of skills, trainings, support for finding new partners or funding mechanism, and so many other services. And this is thanks to the cooperation of several partners in this project, mainly research centers and clusters based in Wallonia. You will have later the presentation, so you will have all the contact persons. Here you have person to be contacted by kind of service, or in this slide, you also have a person to be contacted by the expertise. As I said, you will receive the link of the replay as well as all the presentation. So that's all from my side. And now I will let our first speakers to take the floor and introduce himself. It's Mr. Jens Brandenburger from BFI. Thank you.
Thank you, Lucrezia. Exactly 10 minutes. Perfect. Okay, my name is Jens Brandenburger. I'm from BFI, Betriebsforschungsinstitut, located in Düsseldorf. We are a research center of the German Steel Institute, VDEH, and we are doing applied research for the steel and the process industry. I'm in the Department for Quality and Automation, and we are dealing with the usage of the data, especially of quality data. So, and this is why we have a project, and then this I want to present you today. It's called SurfCon Inspect towards zero defect manufacturing for flat steel production. And you see the partners of this project on this slide. We have BFI, we are a coordinator of this project. We have 2 industrial partners involved. We have ThyssenKrupp, where Yves will tell you about his application in this project in depth. And we have Salzgitter Flachstahl. Furthermore, we have Kersim as a vendor of surface inspection systems from France. Celtic, of course, and we have furthermore a university, Scuola Superiore San Anna from Pisa, doing more theoretical work in this project. But yeah, starting maybe with the application that we have in Andernach, for those don't having this steel background. I don't know. Okay, maybe if you can take over for these slides. You have to unmute yourself.
Great idea. So you will share or I will share?
Yeah, maybe I continue to share.
Okay. Okay.
Try to follow. I try to follow you.
Okay, I'm fine with that. So hello everybody. My name is Yves Unenzer. I am working for ThyssenKrupp Rasselstein in Andernach. So we are located south of Cologne. I am working there for over 25 years now, and I'm the head of the measurement and network department. So let's say about some words about ThyssenKrupp Rasselstein. We are founded in 1760. We are the world's largest production site for packaging steel. So you see that in the picture from above. We are really a big plant. So we have 400 customers in more than 80 countries. We can produce over 1.5 million tons per year, and we have 2,400 employees. Yes, then the next slide we will go. First of all, we go to the production. So let's say we are able to produce coils. We can produce sheets. We can produce scroll sheets, and also narrow strip. That means small coils. So on the other hand, we can have a coating on the strip with tin or with chromium, also with organic coating like foil or the lacquer, let's say PP or PET coated or lac, however our customer want. Also we have one moment, there's a question, I have to read it. It's translated in my case now, and the translation is not easy to understand from the from Teams. So so we are only producing the steel. Our customers are making the cans out of the steel. So we are only producing the steel, and there's we have IF steels. Like I think is the question. So let's go back to our production. Yes, also we have backplate, black plate. That means there's no layer on the steel. We are able to produce widths from 10 millimeters up to 1,200 millimeters. And the thickness is going up from 0.1 to 0.5. And we have a lot of different grades of the thickness and hardness and things like this in our strip. It depends on what our customer wants to do with our material. So here you can see our production. The hot strip you see on the left-hand side, it's produced in our mother company in Duisburg. So we get the material, and in Duisburg, there in the hot mill strip, in the hot mill, there's a surface inspection, of course, in 2D. So we have a lot of information coming from Duisburg for our materials. Then the hot strip is coming into the warehouse in Andernach. Then the first production area is our pickling line. In the pickling line, the surface is getting cleaned from scale. So there's we hope at the end of the pickling line, our material is completely free of scale. And on the end of the pickling line, there is an inspection system in 2D and 3D. We installed it, now I have to think about 4 years ago. And the 3D system is, for pickling line, really a great system because you have no pseudo defects like water, something like that. The 3D channel only sees topographically defects. So that means when you have water, when you have scale, things like that, the 3D channel doesn't see that. It's really helpful for pickling line. And in case of the SurfCon Inspect project, so we use the 3D data to calculate what is a heavy defect or what isn't a heavy defect. Because after the pickling line, we have 2 cold rolling mills, and we want to prevent our cold rolling mills for strip packaging. And one cases in the of SurfCon inspect is to say the cold rolling mill, the defect in the pickling line in our strip, it's not that heavy. So we let it in the strip. The strip is getting cold rolled. Maybe we have a hole in our strip, but it doesn't depend on a strip bag. And the hole, it's getting in the waste and the upcoming lines. Or otherwise, we can say it's a really heavy defect in the pickling line. We have it to cut out because it will cause a strip breakage in the cold rolling mill. I hope it was not easy to understand, but you are able to understand it. Feel free to ask if something is open. So after our cold rolling mill, the ways are there are 2 ways. So we have batch annealing and continuous annealing. So you can see in the continuous annealing, we have 3 continuous annealing lines, and all 3 lines are have surface inspection systems, so we collect a lot of data in the middle of our production, and we can work with this data. So on the other hand, we are looking in the continuous annealing line for scale, and we hope that we get a lot of information there to say in the pickling line, slow down the speed. At the moment, we have no information about the scale in the pickling line. We are working also with the project to detect the scale. But in the moment, we have not that solution for that. We are working with that to detect the scale in the pickling line, a small scale in the pickling line. So yes, then after the annealing area, the temper rolling, we have 3 temper rolling mills. And then our product is coming to the tinning or chromium lines. So I have to think about, we have 4 tinning lines and 1 chromium line. Of course, every line, there is a surface inspection system installed. Also, this surface inspection systems are a part of the SurfCon Inspect project. We want to give our operators at the line information about the quality of the material. So now everybody is thinking, that's not a new thing that we are doing. We want to share the customer data also with the customer. When the customer said, I don't want to have this defect, and a lot of things that we have to do online, not with hard rules, something like that. It depends of the customer and what the customer will do with the product. So you have a lot of things you have to think about that, and that's an online thing we want to do there. Yes, then after the tinning or chromium line, we are able to cut the material, or we can do a PET laminating or lac on the surface. We can do a slitting. Also, we can do a cutting into sheets, and after that, we can lacquer the sheets for himself. Yes, and then when the quality is good, normally we have only good quality, then the material is going up into the warehouse and from there to our customers. So I have to check the questions. Okay, you mean I think if the surface inspection system is inside of our pickling line. So Jens, please go 1 slide back. So there you see the picture of our pickling line. The pickling line is about, I don't know exactly, let's say 100 meters. and you see the area where the word pickling is written. So there you see the acid area, the blue box, let's say it's the acid area. And after the acid area, a looper is coming, and there the inspection system is installed. So we are outside of the atmosphere, of the acid atmosphere. There, let's say, it's really a clean atmosphere. I hope that was the question you have.
Exactly. Thank you very much. My other question was about the quality of the entering material. Do you have IF steel or aluminum kit steel?
No aluminum. And then we have aluminum beruhigt. Aluminium beruhigte Stelle. Jens, kannst du das irgendwie übersetzen? Aluminium, das
Auf
I don't know
Deutsch
the-
auch kann ich nicht verstehen. Können Sie es
Ich
So we
auch
have-
nicht.
einmal probieren? Danke.
So we have IF steels, of course. We have a couple of different steels, but it depends of our customers and what the customer will do with the material. But
the question, excuse me, Yves. The question
Yes.
that is hidden behind is, do you intend also to use such apparatus to detect, for example, inclusion that could cause some other defect that could be visible at the very end of the line?
Of course. We have also non-magnetic inclusion sensors in the end of our process.
Thank you.
So let's say from my side, I think I'm at the end of the. Well, then something else is there? No, okay. So if there are any questions, feel free.
Okay, then thank you, Yves.
Right.
Coming to the project and the project idea, Yves told already some details about surface inspection. Actually, you have the very essential data to assess the quality of a product, especially when you have products that are surface critical to the customer. And we have seen in the past years that we are widely applicable. So you can use that for many applications like decision support, quality assessment, process optimization, or root cause analysis. Anyway, the problem is that they are not easy to handle. For instance, you have here an example where you can see two images from a surface inspection system. The left one is just a streak with no critical influence on the coil, and the right one is a real critical defect. And so the task is here now to differentiate these and to separate these classes. So this is not easy, as you can think. And a second problem is the amount of data that you have. So you have a lot of, this is an example of a coil map. So this is a standard coil with some inspections, and you see a dot for each defect class that is detected by the system. So you have, on each coil, you have a lot of defect, and now it's not easy to say, is it a good coil or is it a bad coil, or is it applicable for the specific customer? And we had an idea in this project regarding towards. Yeah.
Sorry, we have a question here in the room.
Yeah, thank you. I just have a question regarding your previous slide concerning the non-critical and the critical defect. The criticity is based on your customer feedback, because indeed it's very difficult to separate and segregate what is not critical and what is critical.
Yeah, it's based basically on the type and the cause of these defects. So the one is simply a streak of some material that is goes off when you clean the strip, and the other one is an inclusion actually that is flat rolled, but it's another material in that case, and this is critical for the customer. And so he does not allow these kind of defects on the coil.
Okay, so it's based on your customer requirement clearly, because
yeah, it's defined by the process basically. The one it's critical for the final product at the end of the production process. Yeah.
Okay, thank you.
And you
a little question about these two pictures. Is something that is really aware of what is a defect or not a defect is capable to say the left one is not non-critical and the right one is critical, or do you need to have more information than this?
This is exactly the point. Based only on the visual appearance, in my opinion, this is not possible
It's
to
not possible.
separate
Okay.
them, because this system are no magicians. they cannot do things that are not possible for the human viewer and user, and so you will always have separations problems with these kind of defects, and they will confuse them with other critical. So this was the main idea when we want to have zero defect manufacturing, and we do not allow the none of these things on the right side. We have to be able to differentiate them and to separate them from the left one. So, and that was one of the approaches that we had, that we say, okay, we need more data. I will come to this back later. So we will, basically when we say we want to have more data, we have three sources that are possible. We can use further real-time data that maybe allows us to separate critical and non-critical defects. We can use some upstream data that maybe we already know there are some critical defects on this coil or whatever, expecting them and calculating some probabilities if there are some aspects here. Yeah, and we can improve the input quality data regarding the correct separation of critical and not critical defects. This is the main idea, and this is going into our self-inspect framework, where we have some quality online quality processors that are tuned to separate aspects of quality, for instance, different kind of surface defects, but also thickness, coating layers, etc. So every aspect that is possible can have an own quality processor here, and generate quality events coming to a quality supervisor that is selecting them and passes them then to the operator, and as a control action. And this can be done either simply by showing it on a display, but this is the most easy solution. But we also are working on augmented reality applications where we show the defects then directly on the strip, or if you have a really good detection in here in your application, then you can also think about a closed loop control action. This is the basic idea of the project. We want to realize it in its research based on 5 industrial use cases. 3 of them or 4 of them at Rasselstein and 1 at Salzgitter. As Steve already said, we want to use the 3D data to cut out critical defects automatically, to control the speed at the pickling line based on the scale affection is the second use case. Then we have 2 use cases at the finishing lines where we want to do online grading and one use case at the recoiling line where we do support the repair of the coils. How to improve the quality data? You can see here an idea that we basically have. So we want to improve already the input of the surface inspection. That was one of the main ideas, actually, that it works like a hole detector. So a hole detector works like a through light system, actually, and if you see something on the other side, then you know there's a hole. And yeah, we thought that the surface inspection system should work similar, so that you more or less don't even need any classification, because the detection is already reliable enough to separate critical from not critical defects. The second part that we include is also to improve the classification through more and improved training data, and I will tell you something about this approach in my second presentation today. Okay, here are some images of the 3D inspection system, and the first use case that we have here. This is the 3D inspection system installed at the pickling line, and this is an example of a coil break that we have, and this is an example where we have found the critical defect that was responsible for this strip break. And yeah, we use this 3D and as Eve already said, we don't have a problem with the with water, etc., pseudo defect detections, because we are just detecting topographic defects at this part. So this is the first use case input. The second one was the idea that we may use different wavelengths, and maybe we can better separate between different wavelengths between water and critical defects, and used a camera and as you can see here, these are the wavelengths that are reflecting for water and for the critical defect. And we have at about 1,450, we have a higher separation between water and the defects. And so, yeah, we look in this wavelengths now to detect the water, and then we try to separate the critical defects as we know where there is water and where we have a water problem. So to reduce the amount of water defects that are confused with real critical defects. Then we want to increase the amount of training data by synthetic data generation and by providing an open data base. I will show you later, and provide this improved input to have control applications. One you can see here with the cutting control. This is the current result, one of the results that we already have. You can see here, for instance, how the defects are distributed that caused a coil break. The defect that caused the coil break are here in these rectangles, and the defect that not caused the coil break are the cycles. and the size is relative to the real size and the depth of the defects. And our first idea was the nearer the defects are to the edge, the more critical they are for an edge and a coil break. But as you can see here, for instance, you have two defects of the same classification class of almost the same size, and this is far from the edge, and this is nearer to the edge. So, and this caused a coil break. This caused not a coil break. So it looks like that is not as easy as we thought at the beginning. That we thought, okay, we can do a simple rule-based system. So we have to go here a little bit more sophisticated by modeling the outliers that are causing coil breaks. This is the idea. Here is the result about the second use case, about the correlation of speed and scale affection. You can see here the line speed at the pickling line and the scale that was detected at the pickling line and the scale that was detected at the continuous annealing line, so at the end of the production process. So here's obviously there is a correlation between the line speed or the pickling line speed and the scale affection. So this was good for our use case actually. So we thought, okay, we can simply put some areas about the coil and classify each area and count the number of scale defects per area and then control the speed. But we found out that we have a lot of scale at the end that was not visible at the pickling line at all. So there was, as Yves already said, there was a lot of under detection of the scale. And on the other hand, we also had a lot of scale that was detected at the pickling line, but was not real scale detected also at the end of the production step. So we have also a misclassification problem of the scale defects here for this usual 2D system installed at the pickling line. So here we are working on a better sensor that is able to get these kind of 80% already at the pickling line. The grading at the finishing line, there is the idea that this is how it currently works. Usually there is a coil produced in the production, the coil is finished, then there is an automatic rule-based system that says, okay, this coil is good enough or not. And this coil then, this system then warns the operator saying, okay, this coil was not good enough, you have to do something. Then the operator does repair the line, but this affects the next coil. So you have always the beginning of the next coil affected by this kind of warnings. So we now want to go inside the coil, warn the operator already during the running production that is able to fix the problem even before the next coil is coming, and then we have a second coil of good quality. And use case 5, we had tested the applicability of augmented reality devices to show the results and to support the repair at the inspection line. You can see here an image of this inspection line. And one of the first things that we found out was that to use this kind of devices is not that easy because they are quite heavy and you don't want to wear them for 8 hours during your work. So and you have also a problem with the safety because this is razor sharp, and you are not allowed to go too near to the strip. So it's dangerous to have a device here that does not allow you to see everything in the surroundings. So the approach that we want to follow now is to install a projection device here somewhere and to project the defect and the cutting instruction directly on the coil. And we will see how it works. So I was a little bit too long, sorry for that. But yeah, this was quite condensed content of our common research project.
Thank you, Jens. I think there was a question.
Yes. I have a question. I have seen in one of your slides when you talk about defect detection that you have something like a generation of a database of defects by synthesis using a synthesis process.
Which process?
It was
slide you mean?
It was in the slide where you told about the defects. You show the types of defects you can detect. In this, I saw you have synthetic data generation. What do you mean by the synthetic data generation? This is something you generate by creating defects into a software, or it's something you take the defects samples and you modify these samples? So
Exactly, both. Yeah, both for us is in this field of synthetic data generation. This is one example. This is a GAN network that really tries to produce some real synthetic defects, but we found out that this had not that good results than to use real defects that are adapted somehow, so to like mirroring or using different positions of the defects, etc. So to bring some variety into the defect set just by easy operations in the image.
Mm-hmm. So finally, you come back to collection of defects picture and put some augmentation on them by modifying simply the real pictures instead of creating something with let's say it was with some kind of networks like again.
Yeah.
Okay.
Actually, we are now have finished with this database containing only real defects. Yeah, and now we will start using this database and compare the effect of different kind of augmentation approaches to this defect base, so that we can say, okay, this is the best solution for augmentation in this case.
Thank you.
There was also a question in the chat.
Yes, there was a question in the conversation chat.
Exactly. I propose just to raise it directly to the speakers. The idea was just to know if there was a model, an artificial intelligence model behind this defect recognition. I suppose two defects are always different. And the idea is to know how the defect identification is proceeded. Do you just rely on the surface area of the defect and just compare the areas that are detected in order to quote the defects? Or is it a kind of artificial intelligence that relies on more complex models as neuronal networks or Bayesian models, for example?
I will come back to this in my second presentation.
In the next presentation, okay.
Yeah.
Thank you.
See, fine.
Yes.
Okay, so thank you again for joining. And yeah, I am Ismail Mahmoudi. I am a research engineer at CITIC. I work on data management fields, data collection, quality, governance, and so on. Yeah, and my presentation follows on from the slides of Jans, but I will focus on the solution that integrates the classifiers and that process data in streaming way. So I will present my slides. Yes. So I will talk about the challenges, the industrial challenges, and how the solution responds to these challenges. And I will describe a bit the technical approach and the current state of implementation. Then some details about the sharing data through open data. Then I will finally I will just talk about the next steps. So looking at the context of the project, we can identify some main needs or some main requirements. The first one is how to detect the defects in the steel production lines. So we need here surface quality control, and how to optimize the inspection using an AI model, and how to use a classifier with high accuracy and high precision. And the last requirement is how to process data and run the classification in the automated way. So how to enhance the control and the control control to optimize the process speed. So based on this requirement, we can get this specification. So the solution should combine the real-time data capture from the production lines, and the solution should be automated to make the detection and to And the last requirement or the last specification is how to integrate a high precision quality classification. So the impact of this approach, of this solution, it will be on the prevention, on the optimization, and the scalability. So the prevention, because it stops defective strips before further processing. We talk here about the zero defect goal. Optimization because it impact or it enhance the speed, control, and reduce the downtime. So here we talk about reduction or reduced wastes. And scalability because the solution or the robust quality control across production lines, we talk here about a solution that can be enterprise ready. So based on these requirements and specifications, we designed the solution. You can see here the logical view. There is multiple boxes. The first one is how we can capture data in real time. data ingestion and how we can manage the flows. Then the processing, after capturing data, we apply some operation on the images, for example, and some filters on the messages. Then we perform the classification based on the classifiers. Then the results will be stored in database or data house, then exposed to the serving layer, where we can create dashboards and monitoring visualizations. And this data, these results can be useful also for enhancing the models and building the models. Yeah. So with all of these components, there is some internal services for backups and manage user authorization and permissions. So this is just the internal services. Yes. So based on the design we made, some services we developed. So before I describe the services, the development and the test is made in an isolated environment. So the test bed in the infrastructure of CETIC, and it's dedicated to develop the solution itself and to test it before deliver it to the production scenario or production real-world environments. So for the services, there is the first one is for simulating the generation of messages and extracting the images, because the environment is isolated from now. So we developed simulated or simulation service. The second one is data ingestion, the tools to extract and store data. For example, MinIO, which is necessarily compatible, or which is simply object storage system. Then Apache Kafka, which is a tool of streaming, capturing data and deliver it to the next step in the pipelines. The next service is the data processing. So it's the components that process messages and images to run the inference. We have two choices, two options. The first one is Apache NiFi, and the second one is Apache Flink. We'll see later the architecture and the flows. The storage and the monitoring is the last components, where the results of the classification will be stored and exposed to the monitoring with Grafana. So here you can see the flow with the tools. The starting point is the messages and the images from the generation service or simulation service. Then the storage of the images and the messages. Then the classification. So the classification, we can call an API an external system to perform the classification, or it's embedded in the streaming tool. We have two options. The first one uses NiFi, and the second one uses Kafka and Flink. So why? Because we compared the two architecture, and we identified the use case, or we recommend, for example, the first architecture to the phase of testing and developing the model, because it's simpler to manipulate the pipeline with the graphical and drag and drop components. So NiFi helps, or it's dedicated to construct pipelines with the user interface. But the second one is dedicated for the production scenarios, because it's based on code and it requires more careful resource tuning, for example, memory, parallelism, CPUs, and all of that to ensure the parallel the parallel inference. So the second one also it has a lower latency, so it can process and classify a big number of images compared to the first pipeline. Yeah. So here you can see the user interface of the two tools. For example, the first one is for Wi-Fi. You can see the different steps. The steps called processors, and you can see the pipeline. The second one is for Flink. It doesn't give the ability or possibility to construct the pipeline with a graphical way, but just we can consult the resources, the statue of the running or of the inference, and the available resources. Here, I will just present some results based on the available resources. So, for example, to push 100 or 200 images or messages with 3 CPUs and 5 CPUs, for example, for Flink, with the number of slots 3 and 5, we can get, for example, 18 seconds to process 200 images. The second one is Wi-Fi. It has a higher latency, and for concurrent tasks, for example, 3 and 5, we have 45 and 42 seconds for 200 images. So yeah, the difference is clear. One for testing and development, and the second one is dedicated for the real world environment. So here we can see the configuration, just an example for configuration and recommendation. So the configuration of the memory and the number of CPUs, for example, and the task slots. So this to ensure the parallel execution of the classification. The recommendation is about the CPUs allocated. So we should use a number of slots which match the number of CPUs to ensure optimal parallelism. The second recommendation is the amount of the memory allocated to the job. So based on the throughput, based on the volume, the frequency of the images and the events, it will be, so based on that, we can identify the amount of memory allocated to the task manager and the pipeline in general. Yeah, so what I presented until now is the pipeline that execute the inference in streaming. And now the slide is about the open data. So in order to expose data and make it available for researchers to build machine learning models, we selected this tool, which is SECAN. We made an investigation and comparison between many tools, and we selected this one because it's suitable for customization. And we can, for example, add an organization which is circumspect, you see here. And there is 2 data sets. The first one is public. It's the preview, and the second one is the full data sets of images. So it requires login to access to the data. So this is the link. So you can access and create an account and download and access the full data set. Yeah. So in parallel of the pipeline we are developing, we made some tests using one of the tools that belongs to our assets. So at CETEC, we develop assets. One of them is DMWay. So it's a semantic mapping gateway oriented for making processing of data with different data formats, and it's lightweight, and it's suitable to execute processing of data close to the data sources. So we talk here about edge architecture. We made some tests. The architecture is a little bit similar. We have here the sources of data, events, and images. And here we have the streaming tool, the tool that runs the efforts of the model, the classification. With ONX model, which is a packaging of the machine learning model. Then the parallelism that we tested with is 5, and we have a great result, 5 second point 72 for 100 images. Yeah. So for this tool, it's similar or slightly better performance compared to the 2 others. But the added value here is related to the integration with the edge tools, for example, the surface inspection cameras and the sensors. So in distributed architecture here, we can use multiple instances. Each of the instances process data close to the data sources. Here, related to this asset, if you have further questions or you need further information, you can check the link that describes the asset or contact the product manager who is Lotfi Gidar. This is the email of the product manager. Yeah, for the next steps and the improvements that we will work on is related to 3 points. The first one is scalability and testing. So we need to evaluate the solution, the pipelines, and the different workloads. The second one is operating the solution. So we need to support partners to set up and run the solution under real operating conditions in the real world environment. And the last one is adding the last components dedicated for displaying the classification results and configuring, for example, some alerts if we need that. Yes. So thank you, and I will be happy to answer if you have questions. Any questions?
We can go back to Jens.
Okay.
For the final presentation.
Yes, so no questions, and we give back the floor to Jens.
Okay.
Thank you.
Thank you. So my second presentation for this workshop is about the SurfCon Inspect Open Image Dataset. We wanted to have as a new reference for surface classification. Why we do it, and why is good training data so important? So I just displayed here the standard image processing toolchain where you get the images, you have an algorithm chain, usually a detection, segmentation, a feature extraction, and getting some features to separate critical and non critical defects, for instance, and to have a classification on these features, and to get an inspection results. So this is a classical chain. What is deep learning now doing? Actually, you are simply changing the positions of the certain of these components, and you are putting the images and the results that you want to have at the end together. And this is the training data. So the training data is basically your code defining your algorithm chain. And this is why it is so important to have a good training data, because you don't have a good training data, then you don't have a good result. And to answer the question from before, the systems that we are currently apply mainly still rely to this traditional image processing chain. There is a classification, but it's done at the end of the chain. So all the detection, segmentation is done with common image vision algorithms. So pros and cons for this traditional compared to the deep learning approach. The traditional image processing is robust and fast and simple, and you have a full control. So you can at each point of the algorithm chain, you can do anything you want. If you want to apply the feature extraction or add some new features, or simply if you want to have it's more intuitive, as you can, for instance, put some thresholds and directly see the effects that you are thinking you want to have. But there's a high feature engineering effort, what is basically for the part of the surface inspection. It is more or less done because there are already good features for steel images on steel defects available. So this is done. And it's less accurate because you have a problem when you have a high background structure, for instance. Then you have better results for the deep learning as we currently could see. Cons for the deep learning are the high computational effort and the less control of the algorithm chain. So when you want to have deep learning, then what you train is what you get. So you need to have process knowledge. It's important to have a complete training set. It's important to have as less out of the domain data as possible. You have also the problem that you have rare defect events. So when you install a surface inspection, you usually have many dots, pseudo defects, or whatever that are not. There's a question, yes?
Yeah, yes, Jens, can you just tell us whether this classification of outliers, I would tell real outliers, should be supervised by the human eye? I mean, do we have to see the database by our eye and just based on our historical knowledge of process, sort the good and bad data before introducing them into the system, or could it be automatically done?
There are already tools available that do this pre-sorting automatically, but it's when you just use these tools, then you can only see what these tools see, right? So it's always a good point to to verify that you are not in a kind of bubble provided by these filter system that you use at the beginning, right?
Yeah, I understand, because it's you always have the balance between the time you spend into sorting this base, and if you do not have enough data, you will spend less time, but at the very end, you will have not enough data to have a reliable model at the end. And if you have enough data, of course, you will have a good model if you sort the outliers, but at the very end, you will have spent maybe hours and hours just working on cleaning your database. And this could represent a huge time. That's why I raised this question.
Yeah. But yeah, do you have to invest some work actually? In my opinion, this is your source code. And so to do it all automatically with very low effort, you might get not the results that you want to, right?
My question was just intending to ask you if you already applied this deep learning, for example, at ThyssenKrupp, and if so, how much time did you spend on cleaning the database before introducing them into your machine learning system? To have a rough estimation.
This is maybe a question to Yves, right?
Yeah, maybe. Yves is still there?
He spent a lot of time cleaning the data.
Sorry, no. So I'm sorry, what was the question?
Excuse me, if the question was, Jens was just telling us that you need a complete and good training, I would tell into brackets, good training of the database was critical. And in doing so, you have to have a very clean database introduced into the system so that the system can learn efficiently. And the idea was just to ask you if you already made this on your site, how much time did you spend, I would tell, manually to sort the data or to clean the data so that they are complete and effective for your production system?
So, yes, it's not so easy to give an answer of this. It took a lot of time. So you have to know, you have to look at every picture in the database. You have to think about it's a good picture or it's another good picture. So, and when you think about 30,000 pictures, let's say for every picture, 20 seconds, you can calculate how long it will take only to see if the picture is good or not. So
it's a lot. It's a lot at the very end.
Yes, yes. So you are able with our system to collect a lot of pictures. That's not the problem. The step after that, to see or to look at every picture and say it's a good picture or it's a bad picture, this really take a lot of time.
Practically at ThyssenKrupp, you dedicated one people just fully occupied with this, fully busy with this, or for a period of time? Could you tell us a bit more about the implementation, how you did it?
So the 3Ds, also you have to see the 3D system. You have at the beginning not that long time to work. At the beginning, we said only with hard rules. So we said if the defect is bigger than that and deeper than that, then it's a hard defect. So we collected no pictures at the beginning, only hard rules. So the system starting to work really well with not that much of work. The classification we did afterwards within the SurfCon Inspect project. The 2D channel at the pickling line, yeah, let's say at the beginning, we set some thresholds, we collected thousands of pictures, and after that, I did the separation for the classification. Let's say 4 to 8 weeks, let's say minimum at the beginning. So at the beginning, we only collect data, and then sitting in my office and say, "You're good.
Is this good? Is this
Yes.
acceptable? Limit
Yes.
acceptable, etc.
Yes.
Is it orange? Is it red? Is it blue?
Yes, like
Yeah.
that. Yeah.
Okay.
So a pickling line is much more work than a tinning line.
Okay.
That's okay.
Well, that's okay for me. Just please go on, Jens. Excuse me.
No problem. It's a workshop, so please ask. So last point here was how we can evaluate such a model when we have it in the production, and because the problem is you don't know the false negatives, so which defects you don't get. This is always the problem that you have, and currently there is not there are no methods how you can calculate this recall, you call it, without a high effort. So it's always a kind of question mark, and even more than with a standard system where you are mostly based on thresholds for the detection, and then you know, okay, it's about the contrast and which defects you can see and which defects you don't see. With the deep learning, it's even more difficult to determine which defect the system cannot see. So this is one of the main points, and yeah, for the precision, so the true positive, we defined standard procedures. Actually, I was a chairman of VDI group that defines this first standard. Here it is defined how this precision can be calculated even at the line, that you know, okay, which defects it's calculated, which was or is it's classified with which quality. So okay, a lot of classification, and why training data is important. What we did now regarding that in the SurfCon Inspect project is that we, and Ismail already told you, we put this open data architecture. Why we have chosen open data? Because we saw that the data that is currently available to describe the problem of surface inspection is not available, not enough, and the data that is used by the scientific community is even worse. So I can see, and yeah, the second main reason is that especially for the success of deep learning was mainly reason was the availability of large open data sets that everybody can use them to train their own models, and they are free and reliable actually. And it started with this ImageNet, and there's also a Microsoft Coco database and a Google database where we have meanwhile about 9 million images that are not all manually labeled, but a lot of manual labels. So you have a total of 60 million human verified labels on these 9 million defects. So it's an enormous amount of images, and this is why these models get better and better. On the other hand, these databases are not directly usable for industrial image processing, as they can divide between music instruments and sport equipment, but it's not the same to show them surface defects. So we have done an investigation which kind of databases are available in the industrial context. And then you find the first one, basically 12 years old or 13 with 1,800 images and 6 classes and a very low resolution of 200 times 200. But this was the first database available. What is from a Chinese research institute, and there came a Severstal database where we have about 10 times more images, but only 4 classes. And the first realistic database that also had some defect-free images, because this is the most problem, that it's a problem not only to separate defect classes, but it's also the worst problem even to separate background from relevant things. So a good database should also always include some non-defect images. So there was basically a review paper done, which databases are used in scientific literature from 2024. They investigated 333 more papers, and they found even, and at that point in time, more than 30% used this very first database. So when you find in this scientific literature a paper that is saying, okay, surface inspection on hot rolled strip, then it uses in a database for evaluation with only 1,800 images and 6 classes. So this had nothing to do with the realistic, and so we wanted to close this gap between the application of industrial image processing here and the scientific literature. And if you have a closer look, everybody can download this database, and you have already seen some images from surface inspection defects on the real production line, then you even see that they have nothing to do with what happens at the line today. So yeah, this was one of the main reasons that we wanted to also provide an open database to the scientific community with realistic image material and real problems, with a high similarity of different defect classes that I show you in one of my first slides, with a high ratio of pseudo defects and a low ratio of severe critical defects, because this is what happens. Usually you have a lot of nothings and only, so when your production is lucky, only a limited amount of critical defects. So this was the idea, and so enable significant classification improvements, and we publish it under a Creative Commons CC by SA license. And this is an example. We have here 4 defect. We want to have a total of about 31,000 images. We are still collecting, so it can increase a little bit. So this is a distribution. We have 4 classes, 7 classes in total, 4 classes that are critical. So these are real quality relevant classes, and we have 3 different classes that are not critical for the quality of the production. And here you can see some examples for each defect class that we are using, and yeah, we want to publish this database and provide it to the surface inspection community. Okay, any questions?
In your database, there are no entries with clean without defect pictures? I don't. Can you see here? You have not a class for clean?
This is basically in this pseudo class where you can find some background structures, not critical.
Mhm.
Okay, but it makes no sense to provide 10,000
Oh.
images with nothing, right? So these are based on real detections. So at the standardization we call it events. There must be something on the coil that is detected by the system. So there's always an event on the image, and now the classification has to decide which is critical and which not.
Okay. You have a definition of what is an event?
Yes.
Events, you have a definition of it?
We have. You can also look it in the standardization. This is basically something that is detectable by a vision system.
Okay, don't worry. It's thank you.
One quick question. You were talking about the classical algorithms that are used for the image detection. I just wanted to be sure of what you were talking about. You just rely on the classical optical filters, the one, I do not remember the name, it's classical one based on the fact that all the contours of the shapes are drawn in white, the one that rely on the shape of the defect, and the other one based on the surface area, or is it quite different classification?
Yeah, basically the detection just tells you there is something or there's nothing. So segmentation now draws the pixels and separates the pixels from defective pixels versus non-defective pixels within one image. And based on this pixel-wise segmentation, you can calculate different features that may be aligned to the shape of the defect, but also simply the size, or count the number of segmented pixels, or take the mean gray value of segmentation, or whatever you want. So basically, it's all these features are based on a pixel-wise segmentation of the defect within the image. Hoping that it answers your question.
Yeah. Yes, more or less.
I have just one. Do you have a report or something that is published about the results, the algorithm, or of your algorithms? And
we are working on, basically, our project is now in the last year. And we implement the things at the line. So this is the state where we are currently. But in parallel, we are now working on the first publications regarding these topics. Yeah.
There will be publications about it? Or
of course, yeah.
Okay.
We also have a LinkedIn channel and a website where we publish all the things that are available. So
it's up to follow.
It's up to follow. Yes, you're welcome.
Just a question, is it possible to get a copy of the slide?
Yes, I can prepare.
Also, I wanted to add that in the website you can find a link for the open data base or the open data repository. We can also put it here in the chat.
Yes.
Basically,
Is it possible to have the link by mail after this meeting?
Yes, we can add in the. We'll put together all the information and send to the participants.
Thank you.
Okay. Is there any other question? Otherwise, we can go just for a few words conclusion.
Yeah, I can do the conclusion.
Yes.
So thank you very much, Jens, for the presentation. Also, Jens presented in the beginning how the project is structured. We had Yves presenting the problem, the issues, let's say, the challenges of the factory, of the plant in the production, regarding the surface inspection, regarding the types of surface inspection, and how we can benefit from classifying the defects that the inspection systems identify. Then Jens introduced the architecture of and the solution of the project with further details given by Ismail regarding the practical implementation and deployment of all the components that are required for implementing the data flow, and also he gave us some interesting benchmarks regarding the time needed to classify the results, the defects, because also it is one of the requirements is to be a real-time classification. And finally, already Jens initially, then Ismail presented some parts, and Jens finally provided the open data repository that we have put together. The importance of having this open data, this data available for training our models, the importance for the community, and yeah, we invite you all to have a look. And also, if you are interested in, if you are having similar challenges or issues in your work, and you are interested in communicating with us regarding solutions on these aspects, we are very happy to hear from you. Yeah, that's all from our side. There was something on the chat.
Yes.
Just from remark from my side, this is the official definition of event, because we had it in a question that I did not answer. So I now found it in the standard and put it in the chat.
Okay, so.
There is a question from Arno.
Yes.
Yeah, one last question maybe that also looks for the, I would tell, the industrial concern. What would be more or less the installation costs of such a technology? I would tell, as soon as you've got installed, for example, a Parsitech system or something that looks like a camera, what are the costs of installing such a model and train it? Apart from the time you spend in sorting the first database requirements that you need specific to the site, I would tell, on which you make the production of the steel, for example, or any other kind of goods, because it could be also bottles, glass bottles or something like this. The idea is just to have an idea of the cost of the hardware, I would tell, and the software.
Okay, the hardware cost, we don't have it. I don't know if Jens or Yves have more information about the hardware cost, because another partner, Plessing, from the project that manages the hardware of the cameras. Regarding the software, we have used open source software on our site. So it's mainly the costs of putting it together and
But I'm not sure I understand well. Actually, you are trying to develop this solution. You are reaching more or less the endpoint, even if you have some more implementation to make and be sure that it is secured and could be sailed. But the idea, I suppose, is to sail a system like this. After that, for the industrial partners, maybe, or maybe like a private company, or not.
I don't know if Jens want to.
Yeah, but basically, from the research project point of view, we are in a research project, and
Yeah.
so we are only allowed to reach TRL5. So
Yeah.
we are not in the range of a product yet.
Okay.
I would say maybe we will have a follow-up project with a pilot and demonstration, where we develop more the product and the business model of this. Currently, the idea is to have completely open source so that everybody is free to use.
Okay.
But you will sure need some help by some consultancy to install these kind of systems at your plant, right?
Okay. But the plan is to make it full open source.
Yeah.
Okay. That's nice. Thank
you. I would say also we would like to have another project in order to make it more
concrete.
Concrete, yes. Reach a higher tier level, and from there maybe we can investigate further commercial exploitation. Yes.
Okay. Thank you. Thank you very much.
Okay, is there any other question or comment that you would like to share? Otherwise, because we are running 10 minutes late to the estimated time, so I will say that we can close the meeting. Thank you all for the participation. Thank you to the speakers as well. And as said, we will share the replay link as well as the presentations and the link as well. And you will have the contact, so do not hesitate to recontact Jens or here Cetic if you need further information. Thank you all. Wish you a nice afternoon.
Thank you
very
a lot.
much.
Yes, it was very,
Thanks for the
very impressive
presentation.
and very good
Very nice
presentations.
presentation.